So projectile motions. Now we're going to look at something that doesn't move in our straight line. That's how we conveniently use our axis, so that way we can break it up into the horizontal direction, which we'll conveniently call X, and the vertical direction, which I'll conveniently call Y. So we're going to fire a projectile off. Now we'll fire it at some angle to the ground and give it some velocity. And once we let it go, it will scribe a parabolic arc. Of course, this is assuming there's no air resistance and things like that. Okay, so it's a simplified model. In the real world, of course, there is a little bit of air resistance that would come into it, so it wouldn't be a perfect parabola, but it is still pretty close to it, depending on the wind conditions and what have you. Maximum range, whenever you're projecting something, will be when that angle is 45 degrees. That's maximum range along the same level that you sent it from. So what are the initial conditions from this problem? Yes, I just said that it's a velocity of v with an angle of theta. But I want to break that up into what's happening horizontally and what's happening vertically. So when t equals 0, there it is, we draw up, well, it's a right angle triangle, but what it really is a vector diagram. Now, the vector v is what I've drawn here, that blue one with the arrow. So that's the direction we're going. I could have got to the same point by going horizontally and then up vertically. So just like we saw in complex numbers, same idea. We could add two vectors to get a third vector there. All right. Well, we know the angle's theta and we know the hypotenuse is v. So my initial horizontal velocity and my initial vertical velocity I could think of like sides in this triangle. And so just using simple trig, I can see that horizontally it'll be v cos theta, and vertically it'll be v sine theta. Now, you don't have to derive those each time. It is okay to quote that initial horizontal velocity is v cos theta and v sine theta. Displacement, well, it all depends on where you're going to set your problem up. Conveniently, we often just set wherever I'm starting from is the origin. So we're 0, 0. It makes life nice and easy. But you might have a problem where instead of starting on the ground, you might be up a cliff or something. So you might want to change the y displacement to however high above the ground you are or below the ground. You could still set it, if you're up on top of that cliff, at 0, 0. But now ground level would no longer be y equals 0. It would be negative whatever the height of the cliff is. Usually your choice, unless of course they've said show that the equation is this, and then obviously you've got to go with however they've set their problem up. Okay, I've said everything starts with the forces. Essentially that's what I've done here, except I've divided everything by the mass just to get the accelerations. So horizontally there are no forces acting on the particle. Once it leaves my hand, as we saw in that little video before, the only force acting on it is gravity, or the force due to gravity. So horizontally, no forces whatsoever, so there is no acceleration. Vertically, it's that gravitational force, so minus g. All right, if I want to work out velocity, I'm now just talking straight line motion. Two different equations I've got here. I integrate 0, I get a constant. Integrate minus g over the other side, I get minus gt plus a constant. Now what are those constants? Well, we know that when t equals 0, the horizontal velocity was v cos theta, the vertical velocity was v sine theta. So if I sub that in, the constants just turns out to be the initial velocities. So I get x dot v cos theta. Horizontally, it's a constant velocity of whatever v cos theta is. Vertically, it changes because of gravity. So it starts at v sine theta, but then we're subtracting gt. So more time, the more we're subtracting from that initial velocity, and we saw that graph that went down, it just keeps going down at a constant rate. So if I now want to find an equation for displacement, I'll integrate again. So v cos theta is just a constant, so I get vt cos theta plus a constant. y will be minus a half gt squared plus vt sine theta plus a constant. And again, if I sub in the initial conditions, which I conveniently set at the origin, those constants turn out to be 0. So x is vt cos theta, y is minus a half gt squared plus vt sine theta. These, the things I've underlined there, are our equations of motion. We should be able to solve any problem with just those equations. Sometimes they will ask you to derive them, sometimes they will give them to you. If they give them to you, please don't waste time and derive them. Usually after they give it to you, they have put in brackets, do not prove this, or something like that to remind you. But it is okay to quote them if they haven't asked you to derive them. And in an exam or an assessment, I guess the number of marks is the giveaway. Look, all we're really doing here is parametrics. It's exactly the same as we did back in parametrics. Instead of describing the parabola with one equation, we described it with two equations. One for the x value, one for the y value. X was 2at, y was at squared. That's exactly what I've got here if you look at it. X equals 2at. Oh well, 2a in this case is v cos theta. At squared. We've got something times t squared. Oh, there must be some sort of a shift happening or something like that. So it's parametrics under another name. And so that's what I'm saying there. No, look at it. We've actually got the parametric coordinates of the parabola. If you wanted to describe it as the actual equation of the parabola, if you wanted to take time out of it, you could. Just as we did with parametrics, how do you do that? You eliminate the parameter. The parameter in this is time. Time is the parameter. So t would equal x over v cos theta if I rearrange that. Substitute it into the y equation and I end up with a quadratic, which is what we're expecting for a parabola. Yes, the constant looks horrible, but they are all just constant values. So we've got g, we've got v squared, theta was constant. So they are just constant numbers. It's a quadratic equation. So that means it gives you a choice on how to solve things. I could solve things parametrically, or I could go back to the equation of the parabola, use parabola theory to solve the problem. We have choices. And if you wanted to, you can tidy that up. Reciprocal cos squared sec squared sine on cos is tan, makes it a little bit neater. I can change my sec squared to tan squared plus 1. I get a quadratic all in terms with tan theta. Again, a choice. So what sorts of things are they going to ask us? Well, they usually like things like this. Hey, when does it hit the ground? Remember, all you got is those equations to play with. When does it hit the ground? Well, hang on. It must hit the ground. I set the ground to be at y equals 0, so I want to know when y equals 0. What's the range of the particle? How far did it go? Well, once I know when y equals 0, I can get that time and substitute it into x, and I'll find out where it hits the ground. So before I can find out where it hits the ground, I find out when it hits the ground. Substitute that in. If I wanted the quadratic, I could play around with the roots of the equation and go, okay, what are the roots of the equation? So roots of the quadratic would solve the second one. What's the greatest height of the particle? All right, think of the motion of the particle. What happens when it reaches its greatest height? It comes back down, so the velocity must equal 0. Because you can't move in one direction, then move in the other direction without stopping. So that's how we could find it. So we look at that equation, we look at the velocity equation, and we say, hey, when's that equal to 0? We solve that. Then we can substitute into y, and we've got our answer. Of course, that's the vertex of the parabola. If I've got the equation in the parabola, we say, hey, what's the vertex? We can solve it that way. What angle does the particle make with the ground? Now, whenever you want to work out the angles, you've got to go back to the vectors. The vectors are in terms of the velocity. Because we're saying we're travelling this way, then this way. So it all comes down to velocities. So particle hits the ground. I need to know when it hits the ground. Then I can work out the vertical velocity. The horizontal velocity was constant, so I know what that's going to be. But then I can draw a triangle. So now I'm going down. So I've gone down and across. I'll end up over there. There's the angle that would hit the ground. Bit of trig. Tan theta will be y dot over x dot. There often is a little bit of debate about, is it the acute angle or is it the obtuse angle? So what angle does it hit the ground? And a lot of people say, oh, you hit the ground and you say the acute angle. And then others say, oh, but hang on, we've always defined it to be the angle on the positive side. And the reality is they're going to mark both correct, because both are correct. That is the angle that it's making with the ground. It's just you're looking at one side of it versus the other side of it. If I'm talking about the quadratic, what are we talking about? We're talking about the slope of the tangent at that point. So we could go and find the slope of the tangent. Slope equals tan theta, so we're basically getting the same equation. We solve slope equals tan theta. So, in summary, they tell us it's projectile motion. From there we know, okay, it all starts from these two accelerations. If we have to, we can go and integrate and find all the other ones. But I'm allowed to say, but I know my initial conditions of velocity and displacement is, well, that's up to you what you want to set the starting point as. Conveniently 0, 0 comes in nice, but... So let's look at one. Got a ball, throw it with initial velocity of 25 metres per second, angle of whatever the inverse tan of 3/4 is to the ground, work out what's the greatest height. Well, I'm going to need my equations of motion. So let's work out the initial conditions. I've got initial conditions as far as the parabola is concerned. I want to get it horizontally, vertically. So there's my triangle. I mean, you don't have to draw up the triangle. You could just go v cos theta, v sin theta. So x dot equals, subbing in this case, I've got some values for v and theta. So sometimes you'll have values and you'll come up with a nice number, like this one, 20 metres per second. Sometimes they might just leave it in terms of the pronumeral. Y dot, 15 metres per second. All right, let's start. Did they tell me? Oh, I didn't say. A lot of the times you'll notice, just to make the maths easy, instead of you carrying g through, they tell you you can use 10 metres per second rather than 9.8 for gravity. It just makes the maths nice. Not always. Sometimes you have to do it with 9.8, but a lot of times they'll just say, I'll just take 10. So I integrate, work out my constants, sub in and sub in. There's my velocity equations. Integrate again, sub in, and I have my displacement equation. So I now have enough to solve any of my problems. If you hate finding the constants, you could do it as a definite integral. If I was going to do this as a definite integral, what would I do? Well, again, I'd start with the accelerations, but I'd change acceleration to be dv to t. But notice I've used x dot and y dot. Remember, that dot notation we use for motion, but it means the derivative. It's another notation for the derivative, but we usually only use it when we're talking about motion. Separate the variables. The x one's interesting because I've got 0 on the other side. So the integral, even when I multiply, if you like, the dt across, it's still 0. That therefore becomes a definite integral. And look, I really have worked out the constant. It's just that I haven't explicitly done it because it's definite. There's my number. Over on the other one, I can separate nicely at minus 10. With the limits, just match it up. When t equals 0, y dot was 15. I'm trying to get an expression for t and y dot. So I match up the values. Integrate, sub in, move the 15 over, we get the same equation. So now for displacement, well, this time I'll rewrite velocity as dx to t, and over in the other one, dy to t. Separate the variables. Again, match up the limits that we've set. Integrate, sub in, and now I'll do the y one. And we get the same equation. To be honest, it's probably unusual to use definite ones with these because the constants are so easy to work out. But you know, if you want to, you can. All right, let's answer the question. Greatest height occurs, y dot equals 0. So we grab that equation. It's a nice linear equation. So after 1.5 seconds, sub it in to the y value, and we get its height, 45 on 4. I usually write these as a mixed numeral because I just think it makes more sense when you're talking about things like length rather than say, oh, it's 45 on 4 metres. I think it's more natural to say, it's 11.25 metres. It doesn't matter, obviously. If you want to write it as 45 on 4, it's still a correct answer. What if we wanted to find range? Okay, I need to find the time of flight. Notice I've written it down straight away. How do I know? Because parabola is symmetric. So now I'm making use of quadratic theory. I know it's a parabola. If it just took 1.5 seconds to go up, it's 1.5 seconds to come down. Okay? It's symmetric. So time of flight is 3 seconds. Time of flight, I know, is 3 seconds. Be careful with that. That only works if I'm landing on the same level that I've projected from. If I was projecting from the cliff, going to the ground, that's not going to be symmetric. Okay? So when t equals 3, x is 60, so there's my range. Okay, I know it's going 60 metres. All right, after half a second, what's happening? What direction is it going? Well, I know for a start, is it going up or going down? We've got enough information we've found so far to work that out. What are we saying? Got to be going up. Why? Right, because remember we said it took 1.5 seconds to get to the top. So we know it's going up. Let's confirm it. Well, x is constant, y dot, yep, we get a positive number. So we know we're going in the positive direction, we're going up. So if I draw my vectors, which is really just a triangle, so my horizontal one, my vertical one, which makes the actual one, which is the hypotenuse. The values are 10 and 20, Pythagoras, I get 10 root 5. So I know the magnitude of the velocity. Now I just want the direction, approximately, of course, we don't have an exact value for a half, but about 26 degrees 34 it's making there. So, all right, so it's showing at an angle 26 degrees 34 to the horizontal. Okay. Well, what is the Cartesian equation? What is the equation of that parabola of motion? Well, rearrange, make t the subject, it's x on 20. Sub it in, and there's our quadratic, minus x squared on 80 plus 3x on 4. Okay, let's answer all of those, but now let's use the Cartesian equation. Say we want to take it from that approach. So I found the Cartesian last. Imagine if we said, oh, let's find that first. We've got our equation. So the first bit said greatest height. Well, now I'm saying I know it happens at the vertex of my parabola. And rather than work out the x value, remember the discriminant idea? Where we said it was minus the discriminant over, who remembers? Minus the discriminant on 4. 4a. 4a. So for this one, I had to work out the discriminant first, 9/16 over 4a. A, what's a? Oh, it's just a quadratic, coefficient of x squared. So that one I just worked out before, it had a coefficient of -20. So there we go, we get our y value, 45 on 4, same as we got before. Range. Well, hang on, now I'm talking about the solutions to the quadratic. Because the x-axis, if you like, is the ground. So we're saying, where does it cut the x-axis? And we know one solution already, and that's the one that's with x on 4. So the other must be the solution to 3 on 3 minus x on 20, which of course has a solution of 60. So range, 60 metres. The next thing asks us to find the velocity and the direction after half a second. Well, they've put time into this, so I am still going to have to use those parametric ones to get some values. But there's y. I can find the derivative, but I need to know the x value. So going back to the x equation that we worked out, well, half a second was when x equals 10. Now I can use that x value. So the derivative is a half. But the derivative measured the slope of the tangent. That's what we're looking for because we want that angle that it's making. So tan theta is a half, same as we got before, 26 degrees 34. To find its velocity, again, I'm going to have to go back to the parametrics to get the t into it. Now, what's cos theta? We know tan theta is a half, so I just create a triangle over there to work out. Oh, well, 1 on 2, hypotenuse is root 5, so I know cos theta is 2 on root 5. So we get the velocity of 10 root 5. I'm not saying I would do it that way, but I'm certainly saying it's possible to do it that way if you wish to, if you've got the equation of the coordinate. I think probably it's easier to work with the parametrics myself, if you've worked those equations out. Okay, so 3G and 3H in our Cambridge are on projectile motion.